Yeah, I will be speaking about circuit theory and Tamás Roska. And luckily, Professor Churga already mentioned that he was intrigued by the link between fields, circuits, and waves. And I think that circuit theory is the perfect link between electromagnetic theory on the one side, the physical basis of our engineering discipline, and information theory, where we deal with signals and capacity in bits per second and hertz and all that. And sometimes these two disciplines don't talk to each other and have not enough joint endeavors, I think. For me, basically, circuit, as for Tamas, was my first love in engineering. And I have been aware of his contributions to basic circuit theory already before I met him in person. That was during a time when I still was working at Siemens in communication systems and filter design, a lot of practical things, which were important, of course, theoretically, but mainly for the business. And only when I got the offer from the University in Munich to take over the chair for circuit theory and signal processing there, I met him first when he came, when I was in the first year there, to my office and visited me. And then I had the pleasure to personally know him. And that was the start at that time of the cellular neural network topic, which in 1988 has been introduced by this cornerstone publication of Leon Chua together with one of his doctoral candidates, Young. The first CNNA workshop took place here in Budapest in 1990. In 1992, the second one was in Munich, where I was the chairman of. And it takes place every second year. The name has changed a little bit from cellular neural networks to cellular nonlinear networks, and I think now it's cellular nanoscale networks. Possibly there will be another title in the future to come, but anyway, it is an important thing. What I have learned there is that in order to make our circuit models, or system models, even at a higher level of abstraction, to make them physically consistent, is that we have to think about, oh, yeah, I forgot that. You have already seen that photograph already, this group of circuit theorists. I think it was in 1997 at the ECCTD in Budapest. I'm quite sure about that. The European Circuit Theory and Design Conference. And that picture was taken at the home of Tamas. And you see Arpa there. You see Jos van der Walle, who will speak to us in the afternoon. You see Leon Chua there, and Ernie Koo and George Moschitz, many of them. So I was really, at that time, and still am, very proud to belong also to this group of people who were working there. But what I would like to stress now is, when we interconnect different parts of a system, a main concern always is energy flow between different parts of the system. And for calculating energy flow correctly, it's not sufficient to have a single terminal as an input or output of a certain part of the system, and take the squared magnitude of that signal which may be present here and call that energy. There may be no law of conservation for that number which you compute there, and so it would not be justified to call it energy. In order to compute energy, you always need not one terminal, but a terminal pair, a port, with two conjugated variables. It may be voltage and current, it may be electric and magnetic field, it may be velocity and force in a mechanical system. You always need that, and the energy flow must not be positive, it can be negative. It's simply a question of what kind of reference directions I have assumed in starting analyzing a system. So based on that, we have started out to really use circuit theory as a link between electromagnetic theory, which for especially wireless communication is the important thing, and the signal processing information theory part. Later, that there has been a more tutorial exposition of the ideas which we had there. And only recently, I have also been a co-author of a paper which has been entitled Reincorporation Circuit Theory into Information Theory. You see a large number of authors there. The first one is one of my previous doctoral candidates, Amin Mezgani, and the last one is myself. And that's in a new journal which is called BITS, and it's mainly based in the Information Theory Society. So we are really happy that over the time, also people in signal processing and information theory have begun to estimate the important contribution of circuit theory to the overall system theoretic evaluation of our things. And for that, I have not refrained from showing you also a few equations here, and doing that with a topic which has been a hot topic in the last 5 to 10 years in wireless communications, that is so-called reconfigurable intelligent surfaces, or meta surfaces as they are also called. And that picture should show you on the left-hand side possibly a base station with multiple antennas, and then you see down there a no, I can't do that. Let me see a user equipment, a destination, and as it may be always in a urban environment with street canyons, there may be no line of sight connection, even no channel at all between the base station and the user equipment, and therefore such a RIS, such a reconfigurable integrated circuit surface can be a very interesting tool in order to provide a bypass from the base station to the user equipment. As you see there, there are 3 different channels. The channel from the source, the base station, to the user equipment, to the destination, to the receiver. A link from the source to the RIS, to the reconfigurable intelligent surface, and finally a link from the RIS to the destination. And at the RIS, there is only a very simple implementation. Each antenna element there will be terminated only by a lossless reactance. So no complex RF front ends and all that. And by adjusting that reactance which terminates each antenna element, one could really do beamforming and direct the waves to the final user. It's not simply a specular reflection, but it is a reflection which you can control, which you can adapt. And that could be put together in a final equation down here, where you have the 3 channels and a reflection matrix, which tells you that is the one which we can control. We put that into, no surprise, into a multi-port network model, where the box in the center is the propagation environment. On the left hand, you see the voltage generators. That's basically the model for the high-power amplifiers in the transmitter. On the right-hand side, you see a load impedance, and that's basically the place where in the receiver, a low-noise amplifier is always connected to each antenna element. And in the upper part, in the middle here, these Zn, these are the reactances which will terminate the ports where the antenna elements of the reconfigurable intelligent surfaces are. Well, we can describe that with a variety of different matrices. The most common ones are either use impedance matrices or scattering matrices, because, well, in the microwave domain, you can't really measure impedance matrices, but you can measure scattering parameters. But there's no problem. Between incident and reflected wave and voltage and current, there are simple linear transforms between the two, so we can always switch from scattering matrices to impedance matrices and vice versa. This is reciprocal, and therefore the matrices have to be symmetric. The the whole block matrices are shown there. But finally, what we're interested in is to compute what is the ratio between the load voltage at the final receiver and the generator voltage at the transmitter at the base station. And since it's a linear system that makes things very simple, there should be a linear mapping with one matrix from the generator to the load voltage, and we can do it with wave variables also. I have called the one transfer matrix D and the other one H, but basically they should be the same. The funny thing is, when you look in the literature, they derive equations which don't look really to be the same. And that's what I would like to put a closer look at. In order to make things simple, we apply, of course, some approximations. As, again, Arpad has already mentioned, reality is complex, and all the models which we have are only an approximation of reality. But there are good approximations, and one is the unilateral approximation, saying that a signal which comes from a transmitter, from a current in the transmit antenna, induces a voltage in the receive antenna, terminate the receive antenna, there again a current is flowing in the receive antenna, producing a voltage at the transmitter. That is normally discarded, at least as long as we talk about reasonable distances between the two things, that each one sees the other in the far field. And if we have perfect matching, then in the large matrices we have seen, these three zeros here, up there, in the upper right triangular, are due to this unilateral approximation, and on the main diagonal that we have here, scaled identities, is due to perfect matching and gives zeros in the scattering matrix. And there you see the two representations with impedance parameters, with scattering parameters. They have to be equal, as long as we have not made any error in the derivation. And are they identical? Yes, they are. We have been able to show that, but there is one important fact. The so-called direct link from the source to the destination in the scattering parameter representation is not zero if the actual direct link, which I have shown in the beginning, is zero. That is because there is a reflection without any reactances at the RIS, which simply contributes to that. And that is something which has been overlooked in hundreds of publications up to now. And it's only recently, since 1 year, that we have published that people have been aware of that fact. And there are consequences. Due to time, I would not go into details. I would only show you a very simple example, a toy example, actually. The transmitter has only one antenna, the final receiver has only one antenna, and the RIS has only two antennas. Practically reasonable RIS will have hundreds or even thousands of antenna elements, but we can show basic effects with only a very few. Assume that the transmitter is 1,000 wavelengths away from the RIS with its two antenna elements. The user equipment, the receiver, is 10,000 wavelengths away. When we talk about, for instance, 3 gigahertz as a frequency, 1,000 wavelengths are 100 meters. If we go to millimeter waves with 30 gigahertz, then it will be 10 meters only. So these are reasonable differences. And then we have a look at the channel gain between transmitter and receiver, normalized, as a function of the spacing between the two RIS elements. And the spacing is varied here from 0 to 1 wavelength. And the conventional approach, which you find in hundreds of publications, tells, well, the normalized channel gain is simply 1, independent of the spacing between the two RIS elements. And with the physically consistent theory, it shows that it varies from 4 down to 1 and up to 4. So the proper choice of the distance makes a lot of sense to find that out. Okay, then let me come to the conclusions. The description of a RIS-supported MIMO link looks different, whether it's based on impedance or on scattering parameters, but the difference is most striking in the case of a blocked direct link. But that is the important practical case. the risk makes sense there where the direct link is very weak or even absent. But by carefully interpreting the derivations with the aid of circuit theory, we have been able to show that both approaches are describing the same scenario correctly. And the expected power gain of an end-to-end link have been derived, and that opens up a number of even more important questions to make these models physically consistent in a broader sense also. Well, let me come to the final summary. I think we have obtained, with cooperation with Tamas, interesting results and insights into many problems of technical and economical relevance. Again, I would like to stress modeling based on conjugated variable pairs is required to be physically consistent. Therefore, circuit theory multiport models of systems have a central role, and I could only recommend any department, any faculty of electrical engineering and information technology to keep circuit theory in the curriculum. And Professor Tamas Roska, for me, has been a role model in every of the aforementioned aspects, as a scientist, as a teacher, as a mentor, and above all, as a gentle human being and a very good friend. Thank you very much.